All right, here, folks, we are looking at some of the conditions necessary to do a chi-squared test. So we're going to start with this idea of do boys or girls get in trouble more often? Now, of course, we know the answer to this. It's, of course, girls. I don't know. I'm just poking at you guys, see who's responding and listening. Anyways, when we're doing this and doing the conditions, we're also just going to remember and go through a couple of the other ideas as I go through this. So first off, do boys or girls get in trouble more? You're automatically thinking, I hope, to yourself, what are my variables? My variables are going to be boys and girls, and my other two variables are going to be in trouble. I can't spell trouble, T-R-O-U-B. Pretend that says trouble. And the other variable is not in trouble, not T, for lack of a better thing. All right, so when I'm doing my hypotheses, I will say my null hypothesis is always that in a goodness of fit test, that follows what I expect to see happen. And in a case like this where I have multiple variables, I'm going to say that there's no relationship between gender and trouble. And my alternative would be that there is a relationship between gender and trouble. And then I got to go to my conditions. So I start with my conditions, and there's a lot of this is the same. We start with R. Are my boys and girls randomly selected? So in a case like this, I've not told you the context, but yes, we are looking at this, and we've randomly selected 237 boys and girls from within a very, very large city. All right, and let's call them teenagers. So we selected 237 teenagers from a very large city. So they were randomly selected. So we're going to say yes, randomly selected. Again, I'm not doing a very good job here of actually spelling things. Selected, randomly selected as stated. And here's my quick reminder. If they don't say in the problem that they're randomly selected, you cannot say randomly selected is stated. If they don't state it, you can't say it's stated. If they say assume random, then you would say it's stated that we assume it was randomly selected. In a problem where they maybe they don't say anything about randomly selected, you cannot say we must assume random selection. The point of a question like that, they want to find out, do you know and do you recognize that randomization wasn't stated? So in a case where they say nothing about randomization, or either randomly selected or randomly assigned in an experiment, you need to say, in this case, randomly selected students was not indicated, which means I need to assume it was if I want to do this problem at all. Or in an experiment, if they don't say anything about being randomly assigned to different treatment groups, you have to say random assignment was not indicated. It must be in order for us to proceed. Then you can say, therefore, we're going to assume it's random and move forward. But you can't just blanketly say, I assume it's random. That's not good enough. You have to say, if they don't say anything, you have to identify that they did not say anything about randomization. All right, independence is the same old, same old. There are over 2,370 teenagers in big city. Therefore, independent. All right, and the last one is large sample size. Large sample. All right, what do we mean by large sample? I'll show you here in a second. So I'm going to go back up here and I'm going to fill in my numbers. When we looked at this, we had 46 boys who got in trouble, and we had 71 boys who did not get in trouble out of the 117 that were selected. We had 83 girls who got in trouble and 154 who did not get in trouble. Sorry, I got the wrong numbers in there. I had 37 girls. I was going to say those numbers seemed a little bit big, and 83 girls that did not get in trouble out of the total 120 girls. All right. Let's see. There were a total of 154 who did not get in trouble, and there were a total of 83 who did get in trouble when I'm looking at this table. All right. A large sample is that it's actually not all, 80% or more of expected values are greater than 5. And I can do greater than or equal to. In a goodness of fit test, where I just have one row of data, where I'm looking at like colors of M&Ms or Skittles or whatever I'm doing, in a case where there's only one row of data, so there's only really one variable I'm testing. In this case, I've got two. I've got gender, and then I've got trouble or not trouble. But in a goodness of fit test, all of them have to be 5 or more. When I do a test like this where I have multiple rows and columns, then 80% of my cells need to be at least 5. So if I look at this, I've only got 4 cells. So if one of them, if the expected count in one of these is less than 5, I can't do chi-squared because then only 75% would be over 5. So in a case like this, all of them in this case would have to be over 5. So let's do our expected counts. Let's see if we remember. Let's shrink that up just a little bit. So my expected count that's going to go right here is found by doing row total times column total divided by total. All right, so that is 120 times 154 divided by grand total, which is 237, gives me the value of 77.97. I'm kind of running out of room in there. So I need to show that for one of them to show where I'm getting those numbers. So that's 120 times 154 divided by 237. And then I will fill in the rest. So then what I have here is this is 40.97. This is 76.03. I put this little line here to separate out my observed value from my expected value. 77.97, 42.03. And what I have there is I have all cells. Actually, let's not call them cells. All expected values are greater than or equal to 5. Therefore, this is what I always do in all my other tests. Remember, we did other tests and we're like, sigma unknown, therefore use t-test or t-distribution. Proportion test, all conditions are met, therefore use z for proportions. Or for mu, sigma is known, I use z distribution. In this case, we do this, and we're like categorical values, randomly selected, independence, large, all the cells, all the expected values are at least 5, therefore, chi-squared. And as I've said before in class, or if I haven't, I'll say it again here now, I'm not going to say which type of chi-squared test it's going to be, unless you really want to make sure you know the difference. But for the AP exam, just saying chi-squared is safe. You do not have to specify unless they directly ask you which one is it, but which type of chi-squared distribution this is. All right, so in this case, we're doing chi-squared test for independence. We want to know, is getting in trouble independent of gender? Makes sense when I say it out loud. You're like, oh, that makes sense. Is chi-squared independent of gender? All right. So those are the conditions. So in a goodness of fit test where we talk about like M&Ms, and we're talking about blue, yellow, orange, red, green, brown or black or whatever the other color is, all right, do they follow the proportion that the Mars Corporation indicates it should? You know, does the company's, what they claim, does it match up? In a case like this, where I just have one single variable, which is color, in a case like that, all of them have to be at least 5 for expected counts. That number, by the way, is a 5. And again, when we're doing this, it's all expected counts. A common way that they will trick you on a test would be to give you one where they talk about observed values being greater than 5, and that's not part of the chi-squared process to verify conditions. All right? If it's a case where I have multiple rows, maybe I've got 2 or 3 rows of data for variables that I'm comparing, and then I've got another 4 or 5 here. In a case like this, I have a total of 1, 2, 3, 4, 5. I've got 15 cells. All right, and I need to have at least 80% of them. So if you take 80% of 15, you get 12. So times 0.8 is 12. That means 12 or more cells need to be, of expected values, need to be greater than 5. All right, so let's say I'm only talking about expected values here, and I've got 12 and 1, 7, 9, 10, 15, 4, 6, 5, 9, 9, 9, 11, 10, and 7. And then I go through here and I recognize, oh, not all of them are above 5. So this one, is that all of them? Yep. So I've got 2 of them that are not greater than or equal to 5. In a case like that, I can still use chi-squared because I need to have at least 12. In this case, I've got 3, 6, 9, 10, 11, 12, 13 of them are at least 5, so I'm good to go with my large counts. Random sample, independence, large counts. Those are the conditions. I'm not going to show any more in terms of how to do problems. This was only to get you going through and recognizing that you still have to verify conditions when doing a hypothesis test for a squared distribution. So we're still going to have my null and alternative. The null will be that there is no association or no relationship or in a goodness of fit, it follows the pattern or the proportions that the company says, so no relationship. My alternative is there is a relationship, that something's going on. If it's a designed experiment, then I might even be able to show cause-effect. Does certain types of music calm or slow your heart rate down, give you less stress, different things like that. That would be if you did a designed experiment, you could say, yes, these types of music or these types of songs or these types of beats per minute, so do faster songs or slower songs calm you down, or level of stress or however you measure it. If you design experiment, randomization, replication, control, you can go ahead and start proving some of those things. But then we have my conditions, which are randomness, we have independence, and we have large sample size. And then you will have your formula. So it's state, plan, do, chi-squared equals sum of observed minus expected squared, all over expected. You show that for at least one of the cells. Mistakes I see is people forget this symbol, where they just block that off and maybe you don't have it at all. And in a case where they don't have it at all, so let's say this isn't here at all, you would not get credit for the do phase. Because if you just do this and only do one of them, and not add them up, or if you add them up, but this is the formula to show, we're going to look and say, no, that's not what the formula is. So you have to remember that this summation symbol goes in there. And then we conclude. The likelihood of this happening by chance was 3%, which is significant. Therefore, we can conclude that there is a relationship between gender and whether or not you get in trouble. But what I want you to do is actually I want you to go back and calculate out the chi-squared value for those 4 cells. Put that in the reflection response. You do not have to interpret it. I just want to know that you can calculate those values out. So you're going to have to go back, plug in the observed minus expected, squared divided by expected, write those 4 numbers, and then add them all up. There is a way to do this on your calculator, which we'll be doing later, just not right now. That's it. I'll see you in class.